Hi there, my name is Bryenton, and I will be taking you through the overview of the Bryenton culvert design. The given project was designing a culvert for the proposed soccer complex at station 100 plus 25. It was just a culvert that would connect under the roadway to the existing stormwater pond. As you can see, it's a one-way road into the complexes, so this meant that the culvert needed to be designed for a 50-year storm event. The reference materials used for this project were the FDOT Drainage Manual, the FDOT Drainage Design Guide, the FHWA Hydraulic Design of Highway Culverts. The culvert was designed using the rational method, so first we needed to find a composite C value between the C of the turf field area and the offsite area, which gave us 0.21. You can see the calculation in the bottom right. The rainfall intensity was found in the FDOT Drainage Manual for a storm duration of 18 minutes in Zone 7. The area was the turf field area of 10 acres plus the offsite area of 1 acre added together, and the adjustment factors were industry standard values. All these multiplied together gave us the peak discharge values, and the tailwater values were found in the master stormwater report for the complex. Next, the following calculations were made using the peak discharge from the 50-year storm event, which was 21 CFS, which would be the flow per barrel. The headwater depth was found in chart 1B. The fall was 0 because the culvert's right on grade. The elevation of the headwater is calculated using that equation. The tailwater was found in table 2 for 50-year storm event. The critical depth was found in chart 4B. Depth of tailwater was 2 feet. The entrance loss coefficient was 0.5, which was found in table C.2 for concrete pipe with head wall and square edge. The head was found in chart 5B, and finally the elevation of headwater was the invert elevation plus the head plus the depth of tailwater. And lastly, the outlet velocity was calculated using the bottom equation. After the previous calculations were made, we had to check that they followed the constraints given, which were first, the control headwater must be less than or equal to the allowable headwater elevation, which was 53.75 feet, and for the cover depth, the top of the pipe elevation must be less than or equal to the maximum top of pipe elevation. The first draft we tried using a 24-inch RCP pipe, which gave us a control headwater of 54 feet, which exceeds the maximum control headwater of 53.75 feet. So we decided to upsize and try a 30-inch pipe, which gave us a control headwater of 52.63 feet, which is under the max control headwater, so that works, and we found the outlet velocity to be 4.63 feet per second, and we sent this draft away to be approved. The first draft was sent back for revision because the 30-inch RCP violates the cover depth criterion, and we needed to try a different culvert design. So for the final draft, we used two parallel 18-inch RCP square edge with head wall barrels. This gave a control headwater of 53.75, which is exactly equal to the maximum control headwater, so that works, and the outlet velocity was found to be 5.62 feet per second. Next, a reliability analysis was done, and it was found that the 500-year storm event would give a headwater of 58.5 feet, which overtopped the maximum by quite a bit. So we did an interpolation between the 100-year storm event and the 500-year storm event. And this gave us that a 211-year storm event would cause the overtopping for this specific culvert design. The hardest part of the culvert design for me was using some of the charts, more specifically chart 4B and 5B, because it was hard to know how accurate I should be, and some of the numbers, like when I hand draw the lines, I wasn't sure if this was exactly where it should be, or if that was exactly the number it landed on, and it made me a little unsure of some of my calculations. Other than that, the design went pretty smoothly, and I think it turned out well.